So this is going to be the first video dealing with Lewis structures, and we'll just go over the basics here to generate a Lewis structure. We'll be looking at a few simple molecules and ions, and at the end we'll look at something known as resonance or resonance structures. So first of all, if we look at the definition of a Lewis structure, a diagram of a molecule showing how valence electrons are arranged. So that's important, arrangement of valence electrons. And so we look at the arrangement of these electrons around typically a central atom. And so we'll see how we get all the valence electrons and how we can determine number of bonds that are formed and then put it all together around a central atom. So let's get started. First and foremost, you should remember how to quickly determine the number of valence electrons. Group number, the IUPAC way, is not really much of a help, but if we go back to a different way of numbering things, that may make a bit more sense to you. So for example, magnesium group 2, Roman numeral 2, has 2 valence electrons, so that would be the Lewis structure for magnesium. Whereas you go something like chlorine group 7, so chlorine has 7 valence electrons, so if we were to do Lewis structure for chlorine, we put electrons around and then we start pairing them up when we have to, and so that's the Lewis structure for chlorine. So you should be familiar with Lewis structures for atoms, so we're just going to put that into molecules. So one of the first things you want to be able to do is determine the number of electrons, and by electrons we're looking at two different things here: valence electrons and total electrons needed for stability. And so when you think about needed for stability, think of your stable octet, or in the case of hydrogen and helium, a duet, or 2 electrons. So most atoms need 8 electrons to have a stable valence shell configuration. Hydrogen, helium only need 2. Okay, so to do this, to determine the total number of valence electrons, we just add up the valence electrons for all atoms. So determine valence electrons using the periodic table, add them all together. And to determine the total number of electrons needed for atomic stability, we simply determine how many each needs for stability, 8 or 2, and add up based on the number of atoms. So we can do a few practice ones here. So valence electrons, total valence electrons in ammonia, we are looking at 5 for nitrogen plus 1 times 3 for the 3 hydrogens. So we have 8 valence electrons. Total electrons for ammonia is going to be 8. For nitrogen, he needs 8, plus 2. Hydrogen only needs 2 times 3, which would equal 14 valence electrons, or total electrons, sorry. So we need 14 electrons to satisfy all the valence shells. We have 8 valence electrons. How about for CO2? Same process. So valence electrons, carbon has 4, oxygen has 6, and there's 2 of them. So valence electrons for CO2 is going to equal 16. Total electrons to satisfy the valence shell is going to be 3 times 8. Each one needs 8, so that's going to be 24 electrons. How about the cyanide ion, Cn minus? So again, carbon has 4, nitrogen has 5, and this charge indicates 1 more electron. An electron has been gained to allow the cyanide ion to be a stable configuration, so we add that in the valence electrons. So valence electrons in this case is going to equal 4 plus 5 plus 1, or 10 valence electrons. Total electrons required to satisfy the valence shell is going to be 2 times 8, which is 16 electrons. So when you see a charge in ion, be it a positive or negative, it indicates electron movement, either gain if it's a negative charge, or plus or lost if it's a positive charge, and that comes into play with valence electrons only. So we don't have to worry about it once we've got valence electrons figured out. So that's the first step. Second thing we want to do then is determine number of shared electrons and by extension the number of bonds. And so this is done again in two simple steps. To determine the bonding electrons, we take the total electrons we determined minus the valence electrons. That gives us bonding electrons. And then to determine number of bonds, we simply multiply that by 2. Bonding electrons divided by 2 because there's 2 electrons per bond. We're talking about covalent bonds here. So from our previous example, we already have some information, so let's get that out there. Now, bonding electrons is going to be, as it says, total electrons minus valence electrons. So that's 14 minus 8, which is going to equal 6 electrons. So therefore, number of bonds is bonding electrons divided by 2, or 3 bonds. So ammonia will have 3 covalent bonds. How about carbon dioxide, CO2? Now, number of bonding electrons, again, simply 24 minus 16, total minus valence, so that's 8 bonding electrons. Number of bonds equals 8 divided by 2, or 4 bonds. And so this is useful to see this in operation because you may not have predicted 4 bonds for CO2. You might have only predicted 2 bonds, that is single bonds between carbon and oxygen, but in fact they're not single bonds. Okay, so that's how you determine bonding electrons and by extension number of bonds. So last thing we want to be able to do is determine the number of lone pairs, and from that we can, number of non-bonding electrons, and from that lone pairs, because lone pairs also have to be shown in a Lewis structure. And that's pretty straightforward. We get our valence minus bonding electrons is going to give us the number of non-bonding electrons, and we simply divide by 2 to get our number of lone pairs. So this is typically done in one step, but we'll just go through the first one. So non-bonding electrons equals valence electrons minus bonding electrons, so that's going to be 8 minus 6, or 2 non-bonding electrons. And so number of lone pairs, LP means lone pairs, is simply 2 divided by 2, or 1 lone pair. Okay, with carbon dioxide, didn't get all of that erased. With carbon dioxide, then non-bonding electrons is going to be 16 minus 8, and so we divide that by 2 to get number of lone pairs. So 16 minus 8 is 8, divided by 2 is 4. So we can quickly calculate 4 lone pairs. And that's it. So now we're able to put it together. So the process is pretty straightforward, and it's laid out here. The one thing I will point out is if you do have to determine the central atom, sometimes you do have to think about that. If you need to determine the central atom, it's generally the least electronegative. But in most cases, it's pretty obvious because it's the first atom listed in the formula. NH3, ammonia, nitrogen is the central atom, has 3 hydrogens bonded to it. CO2, carbon's the central atom with 2 oxygens bonded to it. It's pretty intuitive in that regard. So let's draw the Lewis structure for ammonia. Remember the formula, NH3. And we've already done the calculations for that. Number of valence electrons, total valence electrons is 5 plus 3, or 8. Number of total electrons is 8 plus 6, or 14. Number of bonds, 14 minus 8 divided by 2, so that's 3 bonds. Number of lone pairs was 8 minus 6 bonding electrons divided by 2, which is 1 lone pair. And now we can draw it. So central atom, nitrogen, there it is. Join hydrogen with bonds. It's obviously bonded, and we got to join them. So there's 3 hydrogens off the central atom. And again, we calculated 3 bonds. There they are. 1, 2, 3. Number of lone pairs we calculated as 1, and so that one lone pair is going to go on the nitrogen. So nitrogen now has a stable octet, 2, 4, 6, 8. Hydrogen has a stable duet, 2, 2, 2. Don't forget that a single covalent bond counts as 2 electrons. Whoops. For each atom of the bond. So that's why with nitrogen we count that bond as 2 for nitrogen, but we also count it as 2 for hydrogen. Remember, they're being shared, covalent bonds. Alright, how about carbon monoxide? Formula CO. So valence electrons. 4 for carbon, 6 for oxygen, 10 valence electrons. Total electrons needed to satisfy the valence shells is 8 and 8, 16. Number of bonds, 16 minus 10 divided by 2. So 6 divided by 2, 3 bonds. Number of lone pairs. Remember, this gives us bonding electrons. So valence electrons minus bonding electrons gives us non-bonding electrons. So 10 minus 6 is 4 divided by 2 to give us lone pairs, 2 lone pairs. Now we can draw it. Carbon is bonded to oxygen, obviously, but we calculated 3 bonds. So since those are the only 2 atoms, that must be a triple bond. We calculated 2 lone pairs. Satisfy the carbon octet, we have to give carbon a lone pair, and to satisfy the oxygen octet, we have to give oxygen a lone pair. So again, we calculated 3 bonds. That's a triple bond. Lewis structure for the cyanide ion, we already saw that, Cn minus. Valence electrons, so this is where we need to consider the charge, 4 plus 5 plus 1, 10 valence electrons. Total electrons required to satisfy the valence shell is 16. Each one needs 8. Number of bonds equals 16 minus 10 divided by 2, 3 bonds. So again, you can see what happens here. Number of lone pairs, 10 minus 6 divided by 2, 2 lone pairs. And so now we can draw it. C is clearly bonded to N, but there's 3 bonds, so it's a triple bond, 2 lone pairs, 1 on each of the bonding atoms. And because it's an ion, we have square brackets and the charge. Don't forget that for ions. So the cyanide ion. Now, last one, sulfur dioxide, SO2. So valence electrons, sulfur has 6 and oxygen has 6, and there's 2 of them, so that's 18 valence electrons. Total required to satisfy the valence shell is going to be 24. Each one needs 8, so 3 times 8. Number of bonds, 24 minus 18 divided by 2 is 3 bonds. And number of lone pairs is going to be 18 minus 6 divided by 2. So 18 minus 6 is 12 divided by 2, 6 lone pairs. So a few more lone pairs on this one. So central atom sulfur, and it is less electronegative than oxygen. Each oxygen is bonded to sulfur, but we calculated 3 bonds. So what does that mean? Well, one of these is a double bond. And now we have to put out 6 lone pairs. So let's start with this oxygen. 2 bonds of the double bond, so it needs 2 lone pairs to satisfy its octet. That oxygen needs 3. Now it has 8 electrons in its outer shell. Sulfur, 2, 4, 6 if you count the bonds. We still have 1 lone pair, so it must go on sulfur. So that's sulfur dioxide, which is a Lewis structure that has 1 double bond and 1 single bond. That's not the end of the story for sulfur, the dioxide, though. Let's just carry on for a minute here. So this notion of resonance structures comes about because a molecule can be represented by more than one reasonable Lewis structure. We just showed that with sulfur dioxide, and I'll show it again in a minute. This is due to the differing only of a location of a double bond. Electrons in the double bond are delocalized, and so the bond can be drawn in different locations. That electron is not fixed to a specific bond. So if we go back and quickly do our Lewis structure, first Lewis structure we did, we put the double bond on the left-hand oxygen, so to speak. But it could have just as easily been between the sulfur and the other oxygen. And so that gives rise to what is known as a reasonable Lewis structure. And if it's reasonable, we have to show it. And so we do show it this way. And so that shows resonance. This arrow, this arrow indicates resonance. So it's either this one on the left or it's this one. It can be one or the other, and it is basically both in equal quantities. So that is what resonance is. You've already seen resonance with benzene. If you recall benzene, and we're going to draw the Kukuli structure for benzene. So those alternating double bonds, well, those are delocalized electrons, and we showed resonance this way. This is the only other possible permutation for benzene because the bonds alternate. And so that is resonance in benzene. Or we just showed this one, singular diagram, which is known as, I think I mentioned this, resonance hybrid. So that's resonance. And that's simple Lewis structures for some fairly simple molecules and ions. And that concludes this video.